Now, what we are doing now, what we are going to explain in this video is related to alternative physical case solutions. We have done it for real roots. So the first step is find out how to find the real roots. The first step is find out natural solution and find out forced solution. These solutions are going to have k parameters in it. So the second step is the calculation of k parameters, and we will be doing these k parameter calculations for real roots, and this video tells you how to do it. Now we are in this second case, which is complex roots. When the roots are complex, how we are going to calculate these k parameters is our video today. So let's go in a bit. We're going to examine the natural solution first, and then we're going to examine the second solution, how we are going to find the k parameters for the forced solution. And there is an alternative shorter for complex roots, shorter calculation for complex roots here. This is steps are the same as we have done it mathematical solution. I'll show you. So if you go to that mathematical solution, go to complex roots, you see here alternative calculation, shorter calculation alternative for complex roots. So that is the one which will be repeated for the natural and forced solution cases. So I'm not going to give any video for these cases, especially natural solution and forced solution. You can examine those in these frames. So this video is going to cover this natural solution, that frame, and that forced solution. Summation of those two is going to give us the general solution. Let's start from the natural solution. So whatever solution we are dealing with, characteristic roots do not change because the A matrix do not change, whether you're considering natural solution or forced solution. So the characteristic roots are the same. We said, so this is, when it is not a natural solution, there is no particular solution. So general solution is the same as natural solution, since there is no particular solution. Remember that natural solution is related when the energy is stored by the initial conditions of the circuit. No independent source included. No independent source means no particular solution. So in this case, my solution, which has a special name, is called the natural solution. So I will be calculating the k values for this case. So in order to do that, we've got to choose the parameter values. Why we need to choose parameter values specifically here? Because we are dealing with complex roots. So we need to choose these parameters. So these parameters has been chosen here. And since it is natural solution, so I'm going to correct it later on. Initial condition here, okay, initial conditions are going to be different. We said the natural solution is the one which depends on the initial conditions. The energy source comes from the initial conditions. So what is this? 1/2 C times Vc0 square is the energy stored by the capacitor. The other energy source could be inductor energy source. That energy is 1/2 L times IL0 square. So there is no independent source in the circuit. So therefore the initial conditions are in here. For this specific example, there is no energy stored on the capacitor, so the only energy source of our circuit comes from that initial conditions of the inductor. So this is the representation of the mathematical model. which represent our circuit, and this is the numerical values. When you choose the numerical values, you end up with complex numbers. These complex roots are complex conjugate each other. The second step, calculate the k parameters. So this is what we are dealing with. So how we are going to do it? So we already said in the mathematical calculation that we need the initial condition plus the capacitor voltage derivative initial condition and inductor current derivative initial conditions. How we are going to calculate it? So it is seen here. If we replace t with 0 in here, you end up with this. So A matrix, sorry, in here I said I made a mistake. So that is the one. Here you are. When you replace t with 0, this is left hand side, which gives out the derivatives of the initial conditions. And then A is this matrix, and VC, replace t with 0, VC 0, and IL 0 is going to be seen here. These two are the initial conditions. These are the initial conditions which is given here. And then, after having done this calculation, that means multiply this with this one, 0. So multiply this one with minus 0.5. You get the dVc over dt when t equal to 0. That means capacitor voltage derivative initial condition is equal to that. So since I've got the capacitor voltage initial conditions and the derivative initial condition, I can calculate this K11 and K12 in this VCT equation. How I wrote this? From this first equation I wrote this. So find the derivative of this function, we get this. So if we replace t with 0, left hand side becomes capacitor initial conditions here, and t replaced with 0, this becomes 1, this becomes 1. So that's the first equation. If we replace in the t with 0, this is the initial condition that we already calculated, which is capacitor voltage derivative initial condition is equal to this one. When t replaced with 0, it's going to be this second equation. So in this second equation, the two equations, two unknown, find the K11 and K12. They are complex conjugate each other. So if you replace K11 and K12 in here and open that S1 and ST as Euler formula, then you're going to end up with that result. And then we're going to repeat it for the inductor current. Find the inductor current parameters, which are K21 and K22. So the resulting function is this natural solution. So left hand side, these are MATLAB results for this differential equation calculation. So this function, here's inductor current change. But there is a mistake here. That should have been 0. That 0 is not there because this is the particular solution. That's not, there shouldn't be any particular solution there. So I'm going to correct it then. But what you see here, the initial condition, the inductor current starts from that minus 0.5, which is the initial condition. So we already know that there would be no instantaneous change in the inductor current. So this is the proof of it. So it starts from the inductor initial condition and goes that way. This signal should be end up with 0. Why is that? Because whatever the energy we've got here comes from the initial condition energy. This energy, a limited amount of energy. So this energy is going to be consumed or absorbed by the resistor, and then there is no any energy source. That is a limited energy we have stored. Okay? Therefore, these functions must go to 0. As you see it, IL goes to 0 and VC T will also go to 0. So if you look at check the initial condition of the capacitor was 0, there is no energy stored on that element. So this function starts from VC0. So you can check those. So these are the graphics, so we can interpret the graphics that way. I am going to correct that mistake. That should not be seen there. But the graphic is correct. You can check that. So this is written wrong here. Why is that? Because when t goes to infinity, this first term becomes 0. So this becomes 1 here. I am saying this should have been 0. It is true in that graph, but the function written here is wrong. For example, what is written here is correct, of course. That's the natural solution. So that should have been put in here. So the second one now, what we have done, show you once more. Complex roots we were examining. So for the complex roots, we examined the natural solution. So next step, we are going to examine the forced solution. Forced solution, the first part is going to be the same as the natural solution case, partly. Why is that? Because the complex roots are going to be the same, the element values are the same. What is difference? For the forced solution, independent source inside the circuit, but capacitor initial condition is 0. When it is forced solution, there is no energy storage on the circuit. So the only energy source comes from independent current source for our example. So the characteristic roots are the same. So the homogeneous solution part is almost the same as the natural solution case. But for the forced solution, we've got to add the particular solution. The particular solution comes from that independent source. So when the independent current source, which is a DC source, 1 amp, this is the particular solution related to that independent source. So we will be calculating these K values in this equation now. So we need the numerical values for that. So if we choose these numerical values here, you see here initial conditions are 0 because we are dealing with the forced solution. Initial conditions is 0, no energy stored circuit. So this is our mathematical model. Numerical one is this. If you find the characteristic equation, from that characteristic equation, we find the characteristic roots, which are complex conjugate roots. So we are going to replace these values for that S1 and S2. So what is left is the calculation of K's. How we are going to do it? We know it. How we know it? So we know the capacitor initial condition. So in the calculation of these K parameters, we are going to use the initial conditions. We already said that. But in this specific case, for this forced solution, initial conditions are going to be 0. So I will be using 0 initial conditions. Initial conditions is equal to 0 doesn't mean that these initials, derivatives initials, are also 0. You could see it here. So that is our differential equation. So if you replace t with 0, you're going to find out the state variables, derivatives, initial conditions, left-hand side. So we put that VC0, IL0 for the first solution, initial conditions are 0 here. So this term is equal to 0. That's true. But this particular solution related term, that is independent source part, is it? This is BUT, isn't it? That's coming from this independent source. When it is forced solution, independent source in. So independent source initial condition when t equal to 0 is going to be put in. So that is going to determine our state variables derivatives initial conditions. So conclusion is that initial conditions of the state variables is equal to 0 doesn't mean that these initial state variables derivatives initial conditions are also 0. That is the counterexample that you see here. So from that, you see for the first one, so the first equation is this, isn't it? VCT is equal to K11 e to the power S12 plus K12 e to the power S2T plus 0. So particular solution is 0. So when you replace T with 0, these are going to disappear. K11, K12 is equal to initial condition. We already said that initial condition is 0, so it is equal to 0. So find the derivative of this function and replace T with 0. We are going to end up left-hand side. This derivative initial condition that we calculated here. So 8 times 10 to the power 6 comes from that. And the derivative functions T replaced with 0 is the left-hand side here. So two equations, two unknown. We're going to calculate K11, K12, which are the complex numbers, complex conjugate numbers. So if you replace these complex conjugate numbers in here, and S1 and S2 complex conjugate roots, we already know it, you end up with a real function like that. So if we are going to do the similar thing for the inductor current, so I'm not going to repeat it here, so you could do it your own. So forced solution graphics comes here now. You see these functions, those two functions start with 0. Why it starts from 0? Both of them start from 0. You see it starts from 0. That means current starts from 0. That's 0 point. And that's 0 point. Why is that? Because we said forced solution is the solution related with the independent source. Initial conditions are 0. So that is the expected result that we've got to observe. So this solution in here, for this specific example, our voltage, capacitor voltage becomes 0. How did I say that? Here you are. This is a sinusoidal function. This is exponentially decreasing function. So because of that exponentially decreasing function, when you get to t equals to infinity, this is going to be 0. So that function becomes 0. But for the inductor current, this is not true, because it is going to be end up with value of a particular solution, which is 1. Here you are, particular solution is 1. So that is the homogeneous part of the forced solution. That's part. That part here, the forced solution, homogeneous part, isn't it? So which comes from this, the second equation here. So that is the graph we have for the forced solution. So if you add this corresponding graphs, natural solution and forced solution, we are going to find the general solution. So here you are, the general solution we found here. Go a bit in detail. When it is mathematical, is this. When it is physical, natural solution plus the forced solution, you're going to end up with that solution, so you can check in. So general solution is equal to natural plus forced. In here, mathematical method, if we use, general solution is the homogeneous solution plus the particular solution. The resulting those two is definitely equal to each other. So we have showed this correspondence for the inductor current. It is also true for the capacitor voltage, of course. So that's the end of this frame now. So we examined now k-parameter calculation for complex roots. So that's the end of this video then.